Good morning, everybody. Thank you for coming out on this wet morning. Just think of the positive. That could be ice or it could be snow. So, 20 below out too. It isn't. All right, a couple things. Please be careful of the camera back there, those of you around there. If it's blocking your view, let me know. I'm experimenting with different camera sites. And let's get back to work. And yesterday I was talking about, you erase this because this was a test to see if the camera could pick it up. And we'll find out. And I think I'll be able to use both boards now. We look at a triple bond, 3 bonds between carbon. 2 of them are pi and 1 is sigma. Pi bonds I can break like that. Sigma bonds, single bonds, you never break. And therefore, I started talking about, at the end of the lecture yesterday, hydrogenation. And hydrogenation, as you know, you have a pi bond. You can break it by reacting hydrogen and a catalyst. The catalyst can be nickel, platinum, or palladium. But I should warn you, I think I already have, organic chemists are lazy. We don't like the balance equations when we don't have to. Unless you're doing charge weights, how much of this and this you have to add to do a reaction properly, we just don't balance equations. So if I have 2 pi bonds, which I do, I'm going to need more hydrogen. I'm an organic chemist. I'm lazy, so I can get around that. Bracket, letters X and S, close bracket. That stands for excess. And that means I have all the hydrogen in the world that will react with anything that will react with hydrogen. So I don't have to worry about balancing it, because I have excess hydrogen. And therefore, for each pi bond, each carbon gets a hydrogen. 2 pi bonds, each carbon of the triple bond gets 2 hydrogens. And therefore, if I do the following, if I take this reaction, and I ask on a test or in real life, what's the organic product or products of the following? And how do you do that? You look at a reaction and say, what's different? What's not a carbon-carbon single bond? What's not a carbon or hydrogen? And the answer is triple bond. Triple bond reacting, oops, I forgot something. Reacting with excess hydrogen, the catalyst platinum. You break each pi bond, each carbon gets a hydrogen, 2 pi bonds, each carbon gets 2 hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 carbons. I better end up with 4 carbons. Here are my 2 carbons of the triple bond. I break both pi bonds. And I get butane. And that's how it works. You could have written that CH2, CH2. And for your fun and enjoyment on this cloudy, rainy Tuesday morning, what would be the organic product or products of the following? right, looks like everybody's done. Before I work on this problem and show you how to do it, I just want to say I'm very proud of all of you. Think about this. This is organic chemistry at its best, where students might say, well, it's organic chemistry, but everybody was trying it, and with a little practice, all of you will be able to do this. All right, let's take a look at this. How do you determine what are the product or products of the following reaction? You look at the starting material and say, what's different? What's not a carbon-carbon single bond, carbon-hydrogen, triple bond? What am I reacting with? Excess hydrogen and nickel, triple bond, hydrogen, excess in a catalyst. And the catalyst can be nickel, as we're using here, platinum, or palladium. We break the two pi bonds. Each carbon of the triple bond gets two hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across. I have a methyl group. What are my two carbons of the triple bond? Right here. Each one, notice I broke the two pi bonds. Each one gets two hydrogens, and you know there are 4 bonds to carbon, so you can put in the rest of the hydrogens. And that's hydrogenation of a triple bond. One of the things students at this point and later in the semester always ask me, Dr. White, do we have any more practice problems? Which I say, sure, do your own. And bring them to me and I'll tell you if you did them right. Well, how do I do that? Here's a secret. When I'm going to do a practice problem like this for you on the board, what do I say to myself? Well, pick a number between 1 and 10. In this case, I picked 4. Do I want to put any alkyl groups on there? Yeah, I'll put a methyl group somewhere on there. What functional group am I testing? This one, for reacting. What am I reacting with? And there you go. Now you know the secret of how I generate problems on the board and on the test. And that's hydrogenation. You've already seen it. Oh, let's do one more because they're fun. I don't want to shortchange you because it came out on this ad weather morning. You cannot have a triple bond in a ring, so I'm not going to do one with a ring. Now why don't you try this one? What would be the product or products that follow? Remember, general reactions are building blocks. Just like a carpenter knows how to use a nail, a screw, a 2x4 to build things, these reactions help chemists, organic chemists, build things. And later in the semester, when we learn more organic chemistry, you'll see some of the things we built that you use in your daily life. You'll be amazed what I can get into, even with the camera on. All right, looks like everybody's done. If you notice from what I said before, I picked the number 2, 4, 6, and I was in the mood for a nice isopropyl group. So you know how I got this example. All right, let's take a look at this. How do you determine what is the product or products that are following reaction? What's different? You can see my hand can't point to anywhere else. Triple bond. What am I reacting it with? Hydrogen excess, and then a catalyst, which can be platinum, palladium, or nickel. In this case, it's platinum. What happens? You break the 2 pi bonds. Each carbon of the double bond gets 2 hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. I have an isopropyl group here. Here are my 2 carbons of the triple bond. Break the 2 pi bonds. Each one gets 2 hydrogens. And you could have written this as CH2 also, and that's how you do it. Question?
Wouldn't that be 2 methyl groups? Because the longest chain is 7,
Hold
not
on.
6.
Yeah, let's talk a little louder. I haven't had a miracle yet, so my ears still work the way they did yesterday.
Wouldn't that be 2 methyl groups? Because the longest chain is 7 instead of 6? With the isopropyl group?
Oh, I don't know. We'd have to name it. Let's do this one. And I forgot that hydrogen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So the longest chain would be 7. This would be more tricky than I put on a test, maybe. But anyway, that's how you do it. And that's part of just learning what's the longest chain. All right, other questions? And again, thank you for your question. Did that answer?
Yeah.
All right, so that's hydrogenation. The other reaction with triple bonds, you sort of already know, is halogenation. Now, when we did double bond plus halogen, you break the pi bond, each carbon of the double bond gets 1 halogen. Well, a triple bond has 2 pi bonds. Therefore, if I'm reacting with a halogen, which is diatomic, and because I'm an organic chemist, I don't want to balance equations. I'm going to use, again, bracket, letter X, S, close bracket, which means excess. I have all the halogen gas in the world to react whatever halogen gas can react with. And in this case, the 2 pi bonds, you break each pi bond, each carbon of the triple bond gets, for each pi bond, 2 halogens, and that's what you get. And the question would be, what's the organic product or products sort of following? And if we look at this and say, what's going on here? I have what's different in the molecule, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, triple bond. What do? React with bromine, gas, excess. Break the 2 pi bonds, each carbon of the triple bond will get 2 halogens. Do you break carbon-carbon single bonds? No. So I have 3 carbons, I better end up with 3 carbons. Those are my 2 carbons of the triple bond. Each one will get 2 bromines. And there you go. Why do you want to put a lot of halogens on things? Well, a number of the molecules with polyhalogenated compounds are less flammable than other organic molecules, and therefore they can be used as flame retardants. Even though about 2-3 years ago, 4 outstanding reporters from the Chicago Tribune did this investigative reporting story that debunked what everybody believes something to be true. That was certain halogenated compounds. They add things like plastic for this monitor, or things like your couch at home, the fabric, help improve the flame retardancy, and that was proved to be wrong. And the other bad thing is certain halogenated compounds are also highly carcinogenic. So, but for sleepwear, a lot of it is a good thing. And I'll let you, oops, I forgot something. I remembered it. What would be the organic product or products of the following 3-point seeds? All right, looks like everybody's done. Let's take a look at this. You know what I'm going to say next. Yes, what's different? You were right. Triple bond. What am I reacting with? Fluorine, one to halogens. Remember, X in this case can be fluorine, chlorine, bromine, or iodine. You break the 2 pi bonds. Remember, triple bond, 2 pi bonds, 1 sigma bond, and each carbon of the triple bond gets not 1, but 2 halogens. You break carbon-carbon single bonds? No. 1, 2, 3, 4, 5 across. I have a methyl group here. My 2 carbons of the triple bond are right there. Therefore, each one gets 2 fluorines. And I've now made that. Now, fluorine is an interesting atom to put on a molecule, besides like the other halogens, to make it flame retardant. Fluorine sometimes will provide certain special properties, such as water repellency, and also make it very slippery, a good lubricant. Teflon, which I think you know in your no-stick pots and pans, has a lot of fluorines in it. And this is one way to have a triple bond in a molecule to get a lot of fluorines into it. So that's a good thing. All right. I think I might have mentioned it, and later today when I get home, hopefully for tomorrow's class, I'll post it on Blackboard, and you'll also get an email, the points breakdown for test number 1. If I remember correctly, it's got 10 pages, and I've got the rest of the point breakdown. But I'll put that down. But the key things is I'll have 1, general knowledge. 2, I'll have nomenclature. Here's the name, draw the structure. Here's the structure, draw the name, or how many carbons in the longest chain. And then the other major area will be give the organic product or products. Now, nobody's ever, and I think I've already mentioned this, is going to pay me to say, Dr. White, if I react that with fluorine, what do I get? No, they'll ask me something like this. How would I make that molecule? Or really, at my level, what molecule would I need to make this sort of product do this, and how do I make it in existing plant equipment? But that's beyond the level of this course. This I call a synthesis problem. And the problem here is give the starting material or materials for the following, 3 or 4 points each. Now, because the Supreme Court, at least up to now, has outlawed cruel and unusual punishment to students, I'll only put one of these on the test, number 1. Test 2 and 3, I usually have 2 or 3. But these are a lot harder. How do you do that? How do you do synthesis? By the way, this is the fun and exciting part of organic chemistry. How do you make something? Well, you look at a molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single? Ooh, halogen. And notice, I have 2 here and adjacent, meaning connected right next to it. Carbon has 2 more. And what am I reacting it with? And I forgot to do this, which I tend to do. I'm reacting it with excess halogen. Well, what do I start with? I learned that reaction, general reaction. These are your roadmaps. They help you go both directions. Therefore, I need a molecule with a triple bond in it. Do you break carbon-carbon single bonds going from here to there? No. So if I end up with 4, I better start with 4 exactly the same way. Which 2 carbons have the halogens? Those 2. Therefore, it would be these 2 would have the halogen. And what's between those 2? A triple bond. Put in my hydrogens, and that's how you do it. Notice if I take this reactor with the excess bromine, I will get that. And that's synthesis. Of all the general reactions I'll be covering for test number 1, I only pick 1 to do a synthesis. Since Dr. White shares the fun, what would be the starting material used to react with excess chlorine to make that compound? And this is the fun part of organic chemistry. At least I think so. That's why I became a synthetic organic chemist. Synthesis is a fancy word meaning to make. All right, looks like, wait, last hydrogen just went down. All right, let's take a look at this. And the question is, what do we react to make that? Well, how do you approach the problem? You look at what you're making and say, what's different? Ooh, 2 halogens, 4 halogens. And notice they're on adjacent carbons. And I'm reacting something with excess halogen gas. What do I start with? Triple bond. You break carbon-carbon single bonds? No. Therefore, I have 4 across plus 2 methyl. I better start with 4 across. Or my longest chain, plus my two methyls. Which two carbons have the halogen? These two. Which will be these two, which are these, therefore a triple bond will be there. And now, and that's how you do synthesis. Now think about what you just tried and did. This is sophisticated organic chemistry, and you can do it. You're getting the hang of it. Doesn't that feel good? It should. All right. One other thing I do want to point out, the strength and power, and in my case I'll say the beauty of learning functional group chemistry, which is what I'm teaching you, is whenever you see a functional group in the molecule, that's how it's going to react, unless there's special cases. And for this class, I'm going to stay away from special cases. So let's take a look at something interesting. And the question would be, give the organic product or products sort of following. And you look at that and say, what do I do? Well, you do the first thing. What's different? I have a double bond. Wait a second. I have another double bond. What am I reacting with? HBr. Wait a second. Dr. White never used excess with HBr. Well, all that means is you have all the HBr, hydrogen bromide, available that will react with anything hydrogen bromide will react with. And what can HBr react with? A double bond. Double bond, HX. X can be chlorine, bromine, or iodine. And I have an extra hydrogen. Is that the one? Did I get both of yours? Yeah, still have a question?
No.
Okay. When it comes back, don't be afraid to ask. So if I look at this, double bond, HX, pi bond is broken, one carbon gets H, the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens, the double bond gets the hydrogen, the other carbon gets the halogen. Do you break carbon-carbon single bonds? No, so I have 1, 2, 3, 4, 5, 6. 1, 2, 3. Let's look at these two carbons right here. Double bond. Which one has more hydrogens? Time's up. Hopefully all pick 2. So the H will go here, and the X will go to the other carbon, which is a bromine. Oh, I've got a double bond here. Same reaction will occur. Which carbon has more hydrogens? That one. 2 is greater than 1. Therefore, the H will go here, and the bromine will go to the other one. And I'll put in my hydrogens. And that would be the answer. You guys see this okay? Is that better? Stage 2. And why don't you try this one for your fun and enjoyment on this not snowy, not icy, not sunny Tuesday morning. What time flies when we're having fun with pi bonds? tricky, but I think you're up to it. By the way, hint, big hint, super big hint. All right, looks like everybody's done. Let's take a look at this molecule. And the first thing you do is what's different? Triple bond. Ooh, 2 triple bonds. What are we reacting with? Excess bromine gas. Triple bond. Excess bromine. And X is fluorine, chlorine, bromine, or iodine. And the halogens, in this case bromine, it's got 2 pi bonds. You break each one, each carbon gets 2 halogens of the triple bond. Well, excess means I've got all the bromine in the world to react whatever bromine can react with. So, do you break carbon-carbon single bonds? No. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here are my 2 carbons of that triple bond. Break the 2 pi bonds, and each one gets 2 halogens. In this case, bromine. I go to the other end, these 2 carbons, right here, same thing, pi bond, break each carbon, pi bond, each carbon of the triple bond gets 2 halogens, in this case, bromine again. And I'm done. And now I've made something that A, will give you cancer probably real fast, or B, also will probably be a good flame retardant. I'd probably stick a few more carbons on there to make it safer. Word to the wise, if you're ever buying a new home, check within a mile or 2 radius of your home that there never was a dry cleaner there, because dry cleaners used to use halogenated solvents, organic molecules, for cleaning instead of water. That's why they call it dry cleaning, because they don't use it. And a lot of them, when they'd have leftover dirty solvent, would go to a field across the street and dump it in the field. In Chicago, there are a couple hundred sites that are considered Superfund sites. I don't know if they finished cleaning up or are in the process or plan to, that are quite dangerous. All right, good news, we finished the chapter. Now, because a week from this Thursday is a test, I'm moving a little quicker than I like to, but I think you're up to it. This Thursday, I will go through the alkenes, alkynes problem set. I think we've got plenty of time today and tomorrow, and we'll get up early Thursday morning to work on it. Now, just like you hopefully have learned the alkane table of 1 through 10 and the alkyl groups, you should know the general reaction, which I've been always writing on the board for your benefit, for each of the reactions I've done. Those are your road maps. How do you memorize them? Write them down and say them 5 times. Or you can use flashcards. That my way works better for me and for a lot of students, but if flashcards work for you, by all means use them. All right, it's a new chapter time, new functional group. And this new chapter is called aromatic compounds. And when we say aromatic, doesn't it sort of sound like the word aroma, something you smell? And it turns out that's how aromatic compounds obtain their name. Aromatic compounds are organic compounds originally isolated, which is a fancy word meaning gotten out of spices and herbs. Example, if you like cinnamon, what you smell and what you taste is due to an aromatic compound. If you, my sister hates cinnamon, I like it. If you like vanilla and things like vanilla extract, that vanillin is a molecule that's an aromatic compound. Same thing with cloves and a number of other molecules from various spices. Now, it turns out, back about the 1300s, 1400s, and so on, because it made food taste better, especially if you had no refrigeration, you wanted to eat something the second day, and it's starting to smell a little gamey or taste gamey, or you put a lot of spices on it, you could still eat it, maybe not get sick. And because of that, spices were highly treasured. Think about it. How did America get discovered by Columbus? He was looking for a shorter route to India to do what? To get aromatic compounds, which you call spices. And you look back at the history of the world, back in the 1400s, 1500s, 1600s, even into the 1700s, the great European powers, Spain, England, Netherlands, and other countries were fighting over islands in the Pacific area in Asia. Why? Because of spices. And if you look at what were some of the important things like Marco Polo and others, they were trying to get spices from China and Asia. And therefore, this is an important chapter because this deals with those things, chemicals, organic chemicals in those spices. I should tell you, for many, many eons, an important driving force in chemistry, especially organic chemistry, has been money. If you can make a buck off something, it's important. And at one point, spices, and they still are, important things. Now, it turns out, if you look at these chemicals in spices, which are called aromatic compounds, they have some unusual chemical properties, especially their stability. They don't change or go bad with time, unless you do something really stupid to it. But if you just keep it and store it in a dry place, they stay stable and good. Many of them, not all, but many of them have a ring with 6 carbons and only 6 hydrogens, or less hydrogens. And these are aromatic compounds. When we talk about aromatic compounds, probably one of the greatest of all organic chemists is Kekula. I'm going to turn the switch, we'll just be on the test to the opposition, but this is something you should know about anyways. Kekula was one of the greatest of all organic chemists. Wow, that makes him great. Well, he was the one to propose a structure for benzene. Benzene is the simplest organic compound with all carbons and hydrogens. And what Kekula proposed was the structure. A ring with 6 carbons and 3 double bonds, and they're conjugated. Conjugated is a fancy word meaning alternating. Double bond, single bond, double bond, single bond, double bond, single bond. And this is benzene. And he proposed that he was the first one, and he got it right. Now that alone is a lifetime achievement. When later on in life at some symposium, someone asked him, how did you come up with the idea for benzene and the structure? He said, the night before I had the idea, I had this dream. And the dream was, and by the way, if you know any organic chemist, and you ask them about Kekula, and just say the word, immediately they'll say, this snake dream. And if they don't say that, well, they don't know their organic chemistry that well. Anyways, what was the snake dream? Well, Kekula said at the symposium, I had a dream where a snake was chasing its tail and finally caught up to it and bit it. And it was going in a circle. And you'll see why he came up with that. That alone, like I said, is a lifetime achievement, but he didn't stop there, or maybe before he did that. He was the first one to recognize there are 4 bonds to carbon. That's a lifetime achievement. He also recognized that carbon atoms are connected together in organic molecules by chemical bonds. This is about the 1820s, 1830s, 1840s, and quote unquote, scientists were still saying, oh, you need to use earth, wind, fire, and water, all those things, the magic things, and No, it's things like chemical bonds, and Cacula help lead organic chemistry into what we now know. And he developed that benzene has 3 conjugated double bonds. Here's a picture of them. If you happen to ever see that stamp and it's not too expensive, contact me so I can buy it. I'd like to get it right here. And notice you have a benzene ring on there. This is from DDR, Deutsches Democratic Republic, which is East Germany when this was issued. Since then, Germany now has issued a stamp in his honor too, and if you see that one, let me know too. So I like that for my collection of chemical things. All right, switch still off. Now, Cacula, the term came up with this idea because of what's called resonance. And resonance is when you only move electrons in a molecule. And if I were to take benzene and move the double bond there, there'd be too many carbon bonds to that carbon, so I now have to move it here. And this one I'd have to move it there. And we show resonance, moving of electrons, by a double-headed arrow. Sometimes, like on here, I put brackets, you don't have to. I should change that slide. And the double-headed arrow is not a chemical reaction, but showing electrons are moving. If I could label one carbon 1 and 1, 2, they exist in both forms at the same time. They switch back and forth and keep on moving. And this is called resonance, and this plays an important part in benzene. All right, switch still off. If you look at the p orbitals, where the electrons are in the pi bond of a double bond, you'll see they're above and below the ring of benzene, holding hands. Like, you ever seen kids hold hands in a circle and, you know, play the children's game? Was it Ring Around the Rosie or something like that? And benzene does that. And it turns out, unlike cyclohexane, because of this pi bonds, benzene is flat. Again, switch is still off. If you were to look at the benzene ring, here are the pi bonds, each electron, you can share it between these 2 carbons or the ones next to it. And what it really looks like in real life is this. They're all connected together. Even though we show it this way, it's really this way. And this gives the molecule tremendous stability and makes it aromatic. Coming attraction. How many of you are familiar with the word or this compound hemoglobin? Hemoglobin, the stuff in my blood, and your blood too, is aromatic compound. I'll talk about that later in the semester. All right, switch is still off, but on certain entrance exams, I'll ask you, how do you know if this molecule aromatic? Aromatic means you have 2n plus 2 pi electrons in a ring. And if we look at this, each double bond is 2 electrons, 2, 4, 6. When n is 2, 2 times 2 is 4, plus 2 is 6. That makes this aromatic. I will never ask this on my test. The ACS doesn't either, but certain entrance exams do. Well, I've been told that. All right, switches back on. How do you draw a benzene ring? First of all, let me remind you, this is cyclohexane. If you forget the double bonds or showing the aromatic character, it's not benzene. And I marked it wrong. You can draw that resonance structure, which is a Cacula. I can move the bonds. You can draw it this way. Or if you saw the picture before, when I had the 2 pi orbitals holding hands, if you were looking down from the top, it looks sort of like a donut. And the third way of drawing benzene, or an aromatic compound, is this way. I personally like this or this, because I just think it's cooler than that. That's my own preference. Anyway, on the test, this is all the correct way of drawing benzene. But you have to put the double bonds or the circle inside, otherwise that's cyclohexane. Common mistake on test number 1, so please don't make that. Now, it turns out people have been calling that molecule benzene for a couple hundred years, at least 100 years before almost 100 years before IUPAC came along, which was in 1920, 1918. And therefore, IUPAC, in their infinite wisdom, and they've done this a number of times, saying, we're not going to convince them to call this something else, so let's make that the IUPAC name. Therefore, this is not only what's called the common name, this molecule, the IUPAC name is benzene. Switches on. And so on a test, if I asked you, draw the structure of benzene, you could draw any one of these 3 structures. On a test, I'll probably would draw the structure like this. What's the name? IUPAC name, and that is benzene. Now, I should tell you, benzene is a liquid at room temperature. It's a good organic solvent. And for many years, until they came along with latex paint, that was used as a solvent for paint, like to paint your house, inside or outside. One bad thing about benzene, you inhale it, get it in your lungs, gets in your body, and I'm not a medical doctor, but it rots your brain out and destroys your major organs. Dangerous stuff. Now I'll explain another one. Now, if you put a methyl group on benzene, this molecule has been around almost as long and known as benzene. Instead of calling it methylbenzene, people were always already calling it toluene. How it got that name, I have no idea. But why do we call this a door and not the floor? Why don't we call this a window? Somebody decided at one time that's what we're going to call it. The methyl group on a benzene ring is toluene. Therefore, if I put this, and this is now the IUPAC and has been the IUPAC name, if I put this on test and say give the IUPAC name, it's toluene. Now, toluene, like benzene, this is dangerous, and unfortunately, for many, many years, it was solvent in glue, the key solvent. And what have you heard about in the news, or if you heard about in history? People who sniff glue would get high. This is what was giving them the high. It was also destroying their brain and major organs. And in fact, most foods now have that taken out, I think. I'm not sure. I had my mother's 3rd cousin or 2nd cousin, who I met when I was a little boy, and he was later on in life had been a painter. And because of that, he inhaled a lot of toluene and benzene. And by the time I met him, he wasn't all there. His brain was pretty much gone. Sad. Hopefully nowadays we do this. Now, I'm going to turn the switch off for this molecule. When you have a vinyl group, a double bond on a benzene ring, we call that styrene. And I'll teach you later in the semester, if we put a lot of them together, we call that polystyrene. And that polymer is used for the white plastic cups that are insulating cups, or the cheap white coolers to put your beer or pop into with the ice. All right, listen up. I was nice last week. This week, I no longer will be nice, so to speak. Lab, for those who have lab today or Thursday, you're more than 3 minutes late. I will not let you in the lab. If you forgot your lab glasses or the printed lab, still come to lab, because if you're late, I won't let you in. And, oh, I went a whole 3 seconds over. Sorry. I'll see you tomorrow, or I'll see you in a couple minutes.